Let's now turn our attention to the idea of inverse functions. As usual, let's take a look at some of the main topics that we want to cover in the next several videos. First, we want to be able to verify that one function is actually the inverse of another function, and we want to determine whether a function actually has an inverse function, and then ultimately we want to be able to take derivatives of inverse functions. Now, just as a quick review, this is more of an algebra sort of a thing. Let's go ahead and do a very quick review of just what inverse functions are. Now, remember a function, I can think of it as having a domain. In that domain, I have all my values of x. x1, x2, x3, out to xn. And then I have my function, and go think of it as just some box. If I have a value from the domain that I put into the function, in other words, I'm going to evaluate f of x1, this value is then mapped to some value in the range, where the range of the y values, y1, y2, all the way out to yk. So this value, x1, will get mapped to y1. Now, the idea of an inverse function, the inverse function, which we typically denote as being f with a superscript of -1, that is not the reciprocal. That is not f to the -1. This -1 in the superscript position here actually makes reference to the fact that it is an inverse function. I should make that really clear. F -1 of x, that's f inverse of 1. That is not the same as f of x raised to the -1, because this is equal to 1 over f of x. This is the inverse of f. Two totally different things. Okay, so if I have this inverse function, which I'm going to think of as another box, what the inverse does is it takes values from the range, puts it into the function, and then it maps it back to the original value of x. Now that's kind of important because, you know, if I have x3 and it goes into the function and it goes to y2, and I have some other value, xn, that goes into the function, and it also goes to y2, that's a function. That is a function. However, this type of function will not have an inverse. The problem is, if I take y2 and I put it into the inverse function, how does it know which of the x's to go to? It doesn't know where to go. So this function that would do this sort of a thing, and then two different x's goes to the same y, that would not have an inverse. Probably a classic example, something like f of x equals x squared. Where f of -2 is equal to 4, and f of 2 is also equal to 4. So I have two different x's being mapped to the same y. So if I were to put this value 4 into what I believe is the inverse function, it won't know which x to go to. So this does not have an inverse function. This idea will lead us in just a moment into a way of testing a function to see if it actually does have an inverse or not. Now, a function g is the inverse of f, if and only if. I don't know if I've introduced this notation or not, but the IFF means if and only if. It's like a one-way implication. This can happen if and only if this occurs. So a function g is the inverse of f, if and only if f of g of x is equal to x and g of f of x is equal to x for all x in the domain of f. That's what inverses do. Now think about it. This one here probably makes a little bit more sense than of any of them. F of x is actually a y value, right? So if I evaluate f of x, that's actually a y. Well, this y is up here someplace. So now I'm taking this y and I'm putting it inside of g of x, which g of x is actually the inverse function. So g of x is actually my f inverse. Well, this better bring me back to the original x. That's what the definition of an inverse is. It just so happens that if g is the inverse of f, then f is also the inverse of g. They're inverses of each other. Now, not all functions will actually have an inverse. And if a function does have an inverse, that inverse will in fact be unique. We won't have more than one inverse function for another function. So if a function has an inverse, that inverse is in fact unique.